Okay. So we start today with the easing model. Now I have a good news and the bad news. I think I took with me, unfortunately, to Brazil an old set of notes. And the good news, well, the bad news that it will, like in this, there is a famous story about John von Neumann being asked at the first ICM after the war to give a talk with the problems for the next millennium, and instead he took with him his old notes from some von Neumann algebra talk and gave a note talk from 4 years before that. And then someone in the first row said very loudly in German that this tastes like reheated soup. And, well, so that's the bad news. But the good news, I thought of writing in newer notes yesterday, but then I figured out that if I improvise here, it will be slower, so maybe people will be happy. Okay, so I will start with a few statements about the easing model. A few general things about the easing model, and then we'll go into the conformal invariance business. So it's actually, I mean, Jeffrey Grimmett has this joke that all the models of statistical physics are people call after their students. So the easing model was invented by Lenz, and for a while it was called Lenz easing model, but then somehow Anzager decided to call it easing model, and it stuck. So the correct probably would be Lenz easing model. So Lenz introduced it. He was advisor of easing, and he suggested to easing to investigate whether there is a phase transition. So it was introduced in 1920. And, well, the model, which was already on transparency 2 days ago, so it's usually played, well, it can be played on any graph. Usually it's played on a grid. So we take, well, a finite piece of ZD. So in our case, it will be Z2, and we usually will take mesh epsilon. So it's, you can think of epsilon ZD, and you assign spins to vertices. And then probability of a configuration of spins is proportional to the exponent of minus, well, plus beta sum over all pairs of nearby vertices x, y, sigma of x, sigma of y. So it's not really important whether you put plus or minus here for the square lattice, because this would just correspond to spins trying to align or disalign. But on a square lattice, there is a trick that what you can do on the square lattice, you can cover it into two colors, and then if you reverse all the black spins and keep all the white spins, then what happens, it amounts to changing the sign of beta. So there is a bijection between what is called ferromagnetic and antiferromagnetic easing model. So as far as spin correlations are concerned, they are not different. If you can solve it with positive beta, you can solve it with negative beta, so it doesn't really change a thing. It changes certain things if you want to study interfaces between clusters. Well, it changes quite a lot. And also, there are other lattices like which are not bipartite graphs, like triangular lattices, where you cannot play this trick. And because of that, there are different regimes there, but that we won't discuss. So we just have this probability of configuration. So this we can denote as, so this can be rewritten as that this is proportion to x to the power number of plus minus pairs which are neighbors. Why? Because here each plus minus pair which is a neighbor will give you the weight exponential of minus beta. So if you have two different spins, and if you have the same spins plus plus or minus minus, you get exponential of beta. So there are only two possible weights per edge. And here the weights you get for plus minus is x, and for plus plus it's 1. So it's sort of easy to make x proportional to, you just take, here what do you have to do? You have to put x equal to exponential of minus twice beta. Okay. So I don't know how much should I go in the background of the Ising model, so I'll do a few things which are somehow motivational for what we are going to do, and also I will do, maybe I'll say, I just skim through the history. So what Ising has proved in his PhD thesis, that in dimension 1 there is no phase transition. So no phase transition for dimension 1. So this is fairly easy to prove. Maybe I will leave this as an exercise. Essentially, what you can see with this definition, that if you put spins on a line and you want to count the energy of some configuration, then you have to count how many edges are there between plus and minus spins. And essentially, when you go left to right, just each time when there is an edge, you flip to the opposite. So once you went a long time, it's really you lose control of what kind of spin you have, because you are just flipping and flipping and flipping. And somehow, regardless x, it turns out that the correlation between spins decays exponentially. So this is very easy exercise. So let's maybe leave it. Should I do it or should? No. Okay. So this is sort of the first appearance of transfer matrix technique, which is more difficult in when you do 2 dimensions, and eventually that led to this. But also the funny thing about his paper, that he made wrong conclusion that there is no phase transition in higher dimensions. So he has a passing remark that the same method, if you do it carefully, works in higher dimensions. And it's interesting that people actually believed him. So if you look at physics literature, people were saying that the reason for real ferromagnetic phase transition is not that there are like small dipoles which interact, but something different, like electrons jumping between atoms or something else. So people, for a while, people couldn't figure out what is the reason. And for example, like Heisenberg introduced a version of this model where spins were not plus minus, but were vectors, by saying that in the Ising model there is no phase transition, so maybe this has to do not with plus minus, but with the fact that there is like orientation in the space. And the funny thing that the phase transition, like in real magnets, it happens in the Ising model, but it doesn't happen in the Heisenberg model. So it's the other way around. So this had to wait for some time. So people indeed introduced several models. So Pyrrhus in 36 proved that there is a phase transition in the phase transition. So he proved it for d equal to 2, but essentially his method works for bigger values of d. And he was he somehow was just counting the perimeters of the clusters, how many clusters possibly you can have of certain size and how long their perimeters would be. So it's just a careful counting argument. And then somehow people believed that there is a phase transition. And the next break came when people understood that this system is of sorts integrable. So this was the Kramers and Vanier paper. So actually, Jeffrey Grimmett has another story about Pyrrhus also, that he had once to introduce very old Pyrrhus to someone at a party, and he says, this is the famous Pyrrhus who proved that there is a phase transition in the Ising model. And Pyrrhus looked at him very angry and said, that's not the only thing I did in my life. And the interesting thing, actually, there is another thing. So he is, in a sense, responsible for the atomic bomb being developed, because there was this famous letter of Einstein and Seward where they suggested that there should be possibility to develop atomic bomb, and they did some estimate of the critical mass, and their estimate was about 5 tons. So if you read the letter, you can find it on the web, it's declassified since then. There is a very nice musing about, well, not very nice, a bit macabre, that you should build a big ship, big nuclear ship, which would sail to Germany and blow it up to pieces. Because, I mean, if the bomb weighs like 15 tons, then you have to build a ship for it. And then what Peirce observed that actually so he had a fairly accurate calculation of critical mass, that it's about 5 kilograms. And when he sent his letter, actually administration reacted and started the Manhattan Project. So, okay, so the Kramers 1 year, they found, so that was 40, so there was a series of papers. So they find that on Z2, phase transition happens, phase transition at X critical. So we have seen pictures 2 days ago, well, basically what it means, so I explained back then what is how one possible definition of the phase transition. So what happens is that if you take, for example, you take a big box with O plus boundary conditions, and you ask what is the expectation of the spin in the center, and if X is smaller than critical X, then most likely the box will frozen, and as the size of the box tends to infinity, the inside will be frozen, so everything will be of the same spin with a big probability. On the other hand, if the temperature is high, then it's the opposite, so it will have no effect on the center. So that's what were the pictures there. So for us, what is important, we will work at this value of X, but we will never use that it's actually critical. So in a sense, when we establish that there is conformal invariance at this value of X, one can deduce that it's critical a posteriori from that. So we won't use that it's critical. We will use certain observations which are equivalent to Kramers 1 year initial observation that this value is self-due, but we don't use criticality. So because of that, I don't want now to muse more about what criticality means. Okay, and theoretically, we also expect, as I said, we expect that in the case of high temperature, we also have the whole critical regime when the temperature is bigger than the critical, and it should be the same as pictures for percolation, but here we don't have a proof yet. So that would be very nice if someone manages to get a proof. And then the next shock was when Ansager, at one of the first conferences after the war, announced that he actually was able in two-dimensional case to calculate several things. So there were papers of Ansager, and then there was paper of Kaufmann, and then Kaufmann and Ansager, and then there is a paper of Young, and then there are many others with many other methods. So for example, one of the particular things they proved is that if you take a box, say with O plus boundary conditions, and you take a box of size n, and you ask what can you say about the spin at the center. So let's say that the expectation of sigma at 0 at the origin, at the center of the box. So they proved that at the critical point at xc, this behaves like n to the power minus 1 over 8. And then it was afterwards, by conformal field theory, this was even more elaborated. So there is sort of a polynomial decaying correlation. So if you have two spins, so we have fixed spins distance n, and this gives us polynomial information about the spin at the center. Okay. Now what happened later, that in dimension 2 there are many different approaches to the Ising model. So if you talk to physicists, usually they would say that it's completely integrable, that it's a free fermion, that basically everything is understood. And this is in stark difference with what happens for dimension 3. So for dimension 3, we expect essentially the same quality of behavior as for dimension 2, but we don't know what the critical temperature is. Probably it's some transcendental number without any particular meaning, and we don't know any exponent. And there is no expectation that it will be exactly solvable in dimension 3. We expect that it's the same behavior and that there is also the renormalization group picture, but the exponents probably are some transcendental numbers. And in dimension 2, it's sort of a difficult story because there is a vast literature, and some of it is physical, yet it can be recasted as rigorous mathematically. So for example, in principle, this theorem, it was never written up as a rigorous mathematical theorem, but to some extent, one could say that most of it is rigorous, though it's never rigorously written. So, okay. Now, what I want to do? I want just to say, because what we are going to do is for the Ising model, but potentially we would want someone to eventually generalize it to other models. So I'll just mention a few possible generalizations. So there is what is called Q-state Potts model. Again, it's invented by Cyril Domb, who named it after his student Potts. So it's Q-state Potts model. So it's, well, let's say Domb and Potts. So this is essentially the same, but you take q possible values of spins. So you take so spins sigma of v, they belong to set of q possible variables. And then you put weight x, you put x interaction if spins are different, and 1 if spins are the same. So you take the probability of configuration being proportional to x to the power number of neighbors which are different, number of pairs VU neighbors, such that sigma of V is different from sigma of U. So if in the Ising model there is, well, apart from the boundary condition, there is a symmetry, you can switch plus and minus spins, then here there is a symmetry, you can do any permutation of the Q spins. Okay, so here well, maybe there are a couple of remarks. Am I writing in big enough letters? Yeah. So one remark is that for q equal 2 you get Ising, and the other remark is so that q2 is the Ising model, and the other remark is that conjecturally x critical is equal to 1 over square root of q plus 1. No, wait a second. Yeah, I think, is it? Yes, yeah, okay. Okay. Now, yes? Can you do it? You go. You can, okay. So it's okay. It's not a conjecture. No, but for all values of q, bigger than 1, and smaller than 1 too. No. Sorry? Well, there is. Well, okay. There is high temperature representation. There is smaller than 1. No, but wait a second. I'm now speaking about Potts model, not about random cluster. For it works. Yeah. Okay. Yeah. Okay. But not from 0 to 2. Well, okay. Well, what? Yeah, but Okay, so the conjecture is that it's true for all values of q, and real positive values of q make sense. So it's not yet. They will make sense in 5 minutes. So it's okay. So maybe we'll make sense of the other values of q first. Let me say that it's called Edwards so-called covering. So this is 1988. What we do, so we will, maybe it's easier to change parameter a little bit. So I'll change parameter x here to parameter 1 minus p. It will work better that way. So, so we take a slightly bigger state space. So now the space will be space of spins on vertices. So this is as in the original Potts model, so that sigma of v are spins. And then we take a cross with the space of, well, let's denote it omega e, on edges where omega are collections of open edges. So, so basically, it's like you should think that there is a percolation model and there is a spin model, and the configuration now is a percolation configuration plus a spin configuration. So it's like a spin so you get things, if you do it for the Ising model, you get things of sorts like this one, and there you add a few edges. So this is an example of a configuration. Okay, and now I have to say what is the probability of a given configuration. So I'll just write the partition function. So it's the sum over all possible configurations. And then the weight of one configuration, you take a product over all pairs of nearby vertices uv. And then there is 1 minus p times the delta function of H being closed, plus p times the delta function of spins being equal. Sigma of u is equal to sigma of v. So this also one can rewrite as sum over all sigma configurations, and then you take 1 minus p to the power number of edges uv such that sigma u is not equal to sigma v. Okay, so basically, well, okay, so what is the weight here? So the weight here is 1 when both of these delta functions occur. So the weight here is 1, where when the H is oh, wait a second, I should have probably put it open, not closed. Yes, yeah. So it's, let me see, it's UV open. Yeah, so yeah, that's the correct one. Yeah. So the weight here. So if the H is closed, then the weight is always 1 minus p. If the H is open, then the weight is 0 if spins are different, and the weight is 1 if the weight is p if spins are the same. So now what would happen, for example, with this configuration? Well, with this configuration, we would get weight, well, okay, an exercise. What is the weight of this configuration? Is it 0 or non-zero? So those are open, open, open. No? Sorry? It's what? Non-zero. Yeah, okay. So, so basically, yeah, because what we get here is that, well, there is a bunch of open edges, and for every open edge, we have that two end spins are the same. So for each open edge, we have weight p, and for each closed edge, we have weight 1 minus p anyway. So here the weight will be p to the power 1 to 3 open edges, and 1 minus p to the power, well, there is 1, 2, 3, 4. So essentially, everything has non-zero configuration as far as we don't have an open edge connecting two opposite spins. So this is what is not allowed. So it's basically like sort of we have a percolation model, and by some stroke of luck, every percolation cluster has the same spin. But it doesn't mean there might be a bigger cluster. So here there is a bigger cluster of pluses, which in the percolation is split into two smaller percolation clusters. So one can recast this as having an Ising model and then running percolation on clusters. Or vice versa, having a percolation model, but then putting spins on clusters, but all clusters have the same spin. So this corresponds to projecting this model to one of the two spaces. And this, let me maybe erase it. So there are two projections. So there are two projections. So first, we can average over omega. So if we average over omega, then we get well, this thing there, which I already, yeah, maybe I'll just copy it so that it's up. So it's 1 minus p to the power number of edges uv, so that sigma of u is not equal to sigma of v. And then also one can average over all spins sigma. And if we average over all possible values of spin sigma, then what we get sum over configuration omega, where we have 1 minus p to the power number of closed edges. Because closed edge, no matter what, gives us a factor of 1 minus p. And then we have p to the power number of open edges. Again, the open edge gives us a factor of p. And then what we have left is the q to the power number of clusters. Because essentially, well, we have clusters, and each of them can take any of the q possible values. Because we are allowed to. Is it? Yeah? Yes. Yeah, sure, because we divide, yeah. And then it means that in this case, for this value, the probability is proportional just to square root of q to the power number of loops. So there is this sort of duality between our FK model and FK model on the dual lattice, because I haven't drawn it here, but one can always think about the dual lattice. One can always think about the dual lattice and the dual model there. So, for example, with the dual configurations like that. Okay. So this means that we don't have p and 1 minus p, so there is this sort of symmetry between dual model and the original model. So for this indicates that this value of p is in some sense after dual. In more generally, if you try to do symmetry, you see that the p changes, because basically we have weight p for open edge when 1 minus p for closed edge, so we sort of change p when we pass to the dual picture. So this indicates that this value is after dual, and let me just, so this value is after dual, and well, self-do. And so I know that this is the theorem. So that it is actually self-critical. It's PC, so P, that the critical value of P is this self-do value of P, which is square root of Q over 1 plus square root of Q. And that's Hugo and Vincent. Yeah, so it's, and this, yeah, okay. But this is kind of indicates, so for us it's not needed in the sense that we don't use any sort of criticality statement, but it sort of indicates that if we want to generalize what we're about to do for the Ising model, then for other values of Q we have to go with this value of Q, which is now certified to be critical, but a priori we don't need this criticality theorem. We could have tried to do it, well, we tried to do it without it. It didn't work though. Okay. Now, let me see. Do I? So I have till when? Till 6:30. So I have. I don't know. I have big. So let me ask organizers. So before I do the spin model, I will have to do the high temperature expansion. Should I do it now, or should I do it because now it fits well with this? Or should I just pass to FK model and then do high temperature expansion later? Vladas is not. Can someone run and ask Vladas? Okay, so let's the question. Do we now work with the FK model and discrete analyticity, or we do something similar for the spin model, which will be needed later? Just do we continue with the same spirit, or we change for a while and we do some discrete complex analysis, not to be overboard? Yeah, let's change the topic. Okay, so this is. Okay, so now we are going to work with this, and we want to find some complex analytic objects in the FK model. And for the spin Ising model, it also these analytic objects, they go via some sort of duality, which is similar to this duality, which is sort of sketched here. So I more sketch what is self-do, not the actual duality. And that duality for the spin model we'll discuss later. So I only want to sort of mention something which we are not going to use, but which is a partial motivation for what is about to come. So this is the nicest formula so far. So we have this model which takes, well, let's say, let me rotate it by 45 degrees. So we look at configurations like this. So the loops might be nested, actually. So let me just draw an example where there are nested loops. And then we say that the probability of configuration omega is proportional to square root of Q to the power number of loops. So it's very nice, simple formula. In a sense, it's simpler than for the Ising model. You just look at the picture, you count how many loops you have. Now, the problem with it is that in the Ising formula, if I have this sea of pluses and minuses, and I cover half of the picture, you can still work with the other half. You can count how many different pairs are there. So you can, if I cover half of the picture, you can compute the partition function in the other half very well. Here, if I cover half of the picture, you cannot really say much, because you see, well, I cover half of the picture, and you see sort of things sticking out. How many loops you have here? Well, you might join so that there are 3 loops, but you might join them so there is only 1 loop. So here the partition function is not local. And Baxter came up with a trick which makes recast it as a local function. And this trick is, again, it's sort of a covering. You add some additional information to this model. So the Baxter trick is to orient loops. So we just randomly orient loops. Well, and then one can do that probability of configuration is square root of q over 2 to the power number of oriented loops. Well, that's not of any help because it's not local either, but it's already, in some sense already, this is something interesting has happened because this looks like a geographic map. Because when we just had loops, it looked like geographic map, but we didn't have a way to know whether this was a mountain or it was a seabed, so it was going down. But once we have orientation, we can say that those are level lines of some discrete function, which changes by 1 each time when we cross a loop. So for example, here it would be, let's say, 0, 1, 2. So it's 0, 1, 0, 1. This is in the opposite direction, so it's -1. It's -1 here, -1 here. So this is, so it sort of means already that the first thing we observe is that there is a bijection between configurations of loops, oriented loops, and functions which change by ±1 whenever we cross an edge. So this is for that reason sometimes it's called as a solid-on-solid model, because you imagine that there is a brick lying in each square, and two nearby bricks, they overlap. So either this brick is one higher or it's one lower. So it's sort of the oriented loops. Loops, they correspond to source functions. So source means here solid on solid. So those are the functions, so that f of u is equal to f of v plus -1 for nearby faces. So if u, v, nearby faces. Okay. And the other part of the Baxter's trick is that what we do, we have here a number square root of q over 2. And we complexify it. So we take, so Baxter's trick for q between 0 and 4, square root of q over 2 is between 0 and 1. And something which is between 0 and 1 is a cosine of something. So we write square root of q over 2 as cosine theta. Or equivalently, we can write that square root of q over 2 plus iy is equal to exponential of I theta. Oops. Uh-oh. Well, I wish the lights would have gone out now. Now, so now what we do, we put this weight for every loop which is counterclockwise oriented, and put the weight exponential of minus I theta for a loop which is clockwise oriented. So the real part always stays the same. So it's square root of q over 2 plus iy, and this is square root of q over 2 minus iy. And then what happens is that if we forget orientation of the loops, so now this is our new complex probability. So this is exponential of I theta times number of loops with orientation. So if the loop is counterclockwise, we count it as +1. If it's clockwise, we count it as -1. And there are two observations about it. So one observation is that when we forget orientation, then we get exponential of I theta for this orientation, exponential plus exponential of minus I theta for the opposite orientation, and this gives us exactly square root of q. So if we forget orientation, we get back our usual model. But if we don't forget, it's sort of, it's not very pleasant because we have a complex probability, and it's sort of, I mean, still the probability of the whole space is 1 because it sums up. When we start summing up, we forget orientation, we get real number. But the problem is that there is lots of cancellations. So the total, so you have a measure so that the total measure of the total space is 1. But the total mass of this measure with this oscillation is much bigger. So this is a problem. If you pass to scaling limit, total mass will blow up. So variation of the measure blows up. But the average mass stays equal to 1. So the situation is bad, but it's not that bad. And you win actually something. And what you win is that this weight is local. And this weight is local because you can calculate this exponential of I theta when you go along your loop. So you can write it as a product of weights, and the weight of the left turn is exponential of I theta over 4, and the weight of right turn is exponential of minus I theta over 4. Now what happens if I do such weights? And then, well, the probability of omega is just the product over all vertices of these weights like that. So what happens if I do weights like this? If I go around the loop, each left turn gives me this weight. Each right turn gives me that weight. And they start canceling out. If I make 2 left turns, 2 right turns, they cancel out. The weight is 1. But once I finish going around the loop, for the left loop, for the counterclockwise, there are 4 more left turns than right turns. So the result will be this to the power 4 exponential I theta as needed. And for the opposite loop, it will be exponential of minus I theta. So the nice thing about the Baxter's trick is that our weight becomes local. And maybe to sort of add related to a bit to the Scott's talk, so one of the physics approaches to this model, which was propagated by Nienhuis, Denis, and others before even advent of the conformal field theory. So it had some conformal field theory built in before it even existed as a subject, was to consider these local weights and consider this height function. And then what you get? You get a random height function with some weight probability which is local. And if probability is local, then it only, and it's also rotationally invariant, this probability, so it only takes into account the gradient of this function, the probability to see some landscape. So then there is a hand-waving explanation. Then when you pass to a limit, what you should get is the free field. Because free field is a random landscape in continuous setting, and it's rotationally invariant, and probability to see some picture only takes into account the gradient. Of course, this reasoning, it's sort of, it's kind of Occam's blade reasoning, that the simplest object of that sort in the continuum is the free field. So when we pass to the limit, we should see the free field. So the logic in the papers of Nienhuis was that we take this function with this complex probability given by that. And then when we pass to the scaling limit, we should get the free field. And that would be a nice thing to prove. I think we are sort of now maybe in a good shape to try to prove it for the Ising model. But in principle, it would be nice to prove. And I want to sort of mention that otherwise, apart from this ansatz, the papers of Nienhuis can be converted into rigorous ones. So calculations he does after that, they use some calculations for the free field. And as we've seen in Scott's talk, one can calculate with free field. So it's sort of well known to mathematicians. So if we would be able to prove this ansatz that this random thing converges to the free field, there would be another way to do calculations parallel to SLE with the free field. OK. So questions? OK. So now what we do, we start the observable for the Ising model. OK. So we want, similarly to the case of the uniform spanning tree, we want to define some sort of discrete analytic function in the Ising model. So again, like there, we have to fix some points in the domain because so that we have non-trivial conformal models, because otherwise we won't be able to define any non-trivial function. And we fix them in such a way which also would set up the things for convergence to SLE. So we want to fix boundary conditions which would give us some sort of an interface which runs between two boundary points. So what we do, yes? Yes. No, these loops should be SLE kappa depending on Q. But you see, this is the thing. So the problem there is that my probability measure is complex. So you see, what can I erase? Let me just erase everything. So my probability measure as defined there. So where did I define the probability measure? Okay, so it's a complex measure. So you can look at it two ways. You can look at a real function weighted by complex measure, and you can weight by real measure and look at the complex height function. And I'm not quite sure which one is correct. But what happens is that if you have an easy case where Q is equal to 4, so if you have Q is equal to 4, then theta is equal to 0. So there is no y parameter, so you just have this and that. Then everything is real, and indeed you get SLE 4. You are supposed to get SLE 4. Now, if you have complex parameters, then you get not exactly the level lines of the Gaussian free field. You get some complex coupling with the Gaussian free field. So it's not exactly the complex couplings which Scott was discussing. It's because Scott was discussing this sort of bosonic couplings where in his setting what happened is that you have an invariant definition of level lines for SLE 4, and when you shift to other values of kappa, the level lines, they become covariant. And they are covariant as a Prepre-Schwarzen forms. When you apply a map phi, you have to add logarithm of phi prime. And this is how he gets different kappas. So here, what you get, you will get what happens with this thing when you do a conformal map. You have these complex weights, and they will change by some complex rotation. So here, the coupling will involve multiplying by some power of phi prime. And if you deal with Q equal 4, you get SLE 4, and everything is nice. If you go off SLE 4, you have a coupling where these are not exactly the level lines of the free field. It's sort of curves which are coupled in slightly different way. But it's not the same coupling as in Scott's talk. I don't know who asked. Ron asked, or yes, yeah. Is it good an answer? I don't know whether Van San or Greg spoke about SLE martingales. So there is this sort of classification of one-point SLE martingales. So this sort of logarithmic martingales, they correspond to couplings which Scott is discussing. And the martingales which are covariant as some power of dz, they correspond to these couplings I'm discussing. And when the covariance vanishes for kappa equal 4, they are the same. So that's more or less the thing. Well, I can, time permitting, I can speak more about it later. It's in the continuous, it all adds up very nicely. Yes, yeah, please.
Does this construction also work if you change the boundary conditions of the spin model at the beginning?
Yeah, it's sort of, well, okay. Let me say that, so my biggest problem with this construction is not in the complex weights, but is in the boundary conditions. So the thing which physicists haven't figured out how to do is how to do this free field reasoning in presence of boundary conditions. So Nienhaus does everything very nicely and correctly on cylinder, on torus, in the full plane, but I don't think we understand very well how to set it up nicely with boundary conditions. So at all, including all the plus ones. So so this setup, this statement about passage to the free field, it certainly makes sense if you are on a torus or in the full plane. If you are with boundary conditions, it makes a little bit less sense. I know what should happen in the continuum, but in the discrete, well, it doesn't quite connect very well. Yeah, so I don't know whether it's a good answer. Okay, so now let's maybe continue. So we want to do some boundary conditions, which I didn't erase. We want to do some boundary conditions which would have a curve built in. So we just do the same game of loops, but besides loops, we run an interface between two boundary points. So what we do, well, we consider, for example, a domain like this. So this is an example of a configuration. So we fix two boundary points, let's say A and B, and we just put source here and sink here. So in the language of the original FK cluster model, this corresponds to what? This corresponds to model, say, living on one graph, and we have wired boundary conditions on these sides, on this side in this graph. So let me maybe finish my drawing. And if we pass to the do model, which is on the do graph, it will have wired boundary condition on the other arc. Yeah, I should have drawn these clusters first, because now they're a bit intersecting with loops. So you can think of this sort of a random cluster, blue random cluster model, which is wired on the upper arc, and the yellow cluster random cluster model, which is wired on the bottom arc. And then there is a unique interface between the two big clusters and some loop interfaces. Or you can think from the very beginning with the loop model, where there is a source at A and source at B. So you just think you erase the clusters and just think about pictures like this. Then again, once again, the probability of configuration is proportional to square root of q to the power number of loops. And we will eventually work with the Ising model where q equal to 2, but the setup is for general q. So okay, and now what we want to do, we define, so definition, so now we want to define a function which will be discrete analytic. So somehow it makes for a nicer definition if we define it on edges rather than at vertices. So the function will be defined at the centers of edges. So for example, here. And the definition is that f of z. So basically, we want to write probability that this interface, let us denote it by gamma. So gamma and interface from A to B. So basically, it's a probability that gamma passes through Z. But then we want to weight it in a complex weight, by a complex weight, well, there are several reasons why we would want to put a complex weight on it. One is this analogy with the Baxter streak, that it makes for a nice model to put complex weights. So we don't need here to put complex weights on loops, but on this we want to put it. And because what, say, Baxter does, he puts complex weight on oriented cycles. And you can argue that this curve from A to B is oriented always in the same direction. So it makes sense to put complex weight on it. So for example, one way you can orient it, you can make two halves which are oriented towards Z. So this is one way to define the observable we are after, is to say that in our domain we have oriented cycles, and then we have two sources where something is incoming. And we have a double sink at Z. And then we count what is the partition function of this. If we would be doing this, we would just count the probability of interface passing through Z. But then we put complex weight on it, and the loops are not important for complex weights because we can forget their orientation. But for this curve, the complex weight will be important because it's always oriented in that way. The only difference is that you cannot really do it like that, because it turns out that the weight, complex weight for a curve should be different from complex weight for a loop. For easing, they coincidentally coincide, but it's just some struck of numerology. But for general model, they should be differently weighted, because this is loop which is just floating freely, and this is a curve which is attached short to the boundary. Okay, so what we do, we take the expectation of the following variable, that Z belongs to gamma. So if we do this, we would have just the probability that Z is on this curve. And then we multiply by weight, which is the exponential of minus I over 2 times winding of the curve gamma from B to Z. So this is winding just of this half of the curve. Well, why I take one half of the curve? Well, there are two reasons to take only one half of the curve. Because the winding of the other part would be the same. So if they start like on the picture, their windings will always be the same by symmetry. And if the other point is at an angle, then their windings will always be different by that angle. And the other one is that eventually we want to relate this curve to a SLE, and then B will be the target point. So we'll start drawing this curve towards B. So it makes sense to count everything with B, because B is immovable. Now, by winding, I mean winding in radians, how many turns it made. So in this picture, it made no turns whatsoever. So you can also rewrite it in terms of how many turns our. So this also can be rewritten as 1 for Z equal gamma. And then you can put weight lambda to the power number of turns of gamma from B to Z with sign. And what should be the weight of a turn? So when gamma makes a left turn, you should put a weight. Left turn is a winding of pi over 2. So you put weight minus I pi over 4, exponential of minus I pi over 4. And when you put right turn, exponential of I pi over 4. So this is lambda. This is lambda bar. And again, right and left turns, they cancel out. Sorry? Yeah, okay, let's maybe put the sigma. So this is what I did is for the Ising model. Now for general model, you have to change 1/2. It's yeah, it's like we were at a talk of Nekrasov recently, where Witten asked a question: what is 1/2? And then Nekrasov was thinking for a very long time, and then he started looking. It was this like 4-story blackboard in Switzerland, and he was looking and said, "Ah, it's there. It's just 1/2." Is that what you wanted to ask? So, okay. So what is 1/2? 1/2 is the spin. So it's sigma equal to 1/2. So I mean, you can just reason combinatorially. Suppose we know this Baxter's trick, or suppose even we don't know. We want to play, we want to find something discrete analytic which measures this curve. What kind of weight we can put on it? It makes sense to put weight which makes factor of lambda and lambda bar for every left or right turn. Why? Because it agrees very well with the SLE. And actually, if you know that it should converge to a SLE, you know you can classify Martingales for a SLE, and you can see what is Martingale, what exact you can have as Martingales for the Ising model, and you would see then what would be the logical value of lambda. Or alternatively, you can just leave lambda and sigma as a free parameter, and then check for which value of sigma you would get discrete analyticity. But somehow, combinatorially, you cannot really put anything more general there. If you want to play with something local, you will see in 5 minutes that anything more general won't do. So we are kind of stuck with that because we need something which has local definition, and these terms, they have local definition because you just go around the curve and you count them. Okay, so the eventual theorem we want to prove. So the theorem is that F is discrete holomorphic. Well, let's say on epsilon lattice, so it's epsilon holomorphic, and solves discrete Riemann boundary value problem. So we'll come in tomorrow to what that means. So it's an easy case of Riemann-Hilbert boundary value problem, which were sort of fashionable lately because of the relation with random matrix theory. But so there usually people speak about Riemann-Hilbert problem. The Riemann-Hilbert problem is finding an analytic function which, when you cross a line, has a certain jump, so that the two values here and there, they are related by multiplying by a number and adding another number. And Riemann problem is just multiplying by a number without adding another number. And then there is a boundary value problem. So Hilbert observed that you can reduce the problem of finding function with this jump by just finding a function in half plane which solves certain problem. And actually, he had a big mistake in his deduction, so it's then Privalov noticed this mistake. So in some literature, it's called the Riemann-Hilbert Privalov problem. But Privalov also made a mistake of his own, so I think it was Arenstein who actually did the first correct proof I've seen. So, but calling it Riemann-Hilbert Privalov-Arenstein problem would be a bit too much, so we just call it Riemann boundary value problem. In Riemann work, it appeared in the theory of tides as a boundary problem for ODEs which were describing tides. Now, it turns out that in the continuous, this problem is solved by an easy function which is a conformal map to a strip. So the other part of the theorem that as epsilon tends to 0, so omega epsilon discrete domain tends to omega, then this function f, well, let's denote again epsilon, tends uniformly inside omega to the function, well, okay, now we have to normalize it as usual. So it tends to a certain specific function, square root of phi prime, where phi is a map from the omega domain to a horizontal strip. And now here I have to, I always mess it up. I think you have to divide by square root of epsilon. Divide? Yes. Okay. So this is the theorem we plan on proving tomorrow. And so essentially there are well, there are two parts. One is discrete part to observe that f is holomorphic and that it has certain boundary value problem. It's slightly more complicated than a Dirichlet problem that it's equal to something, but it can be recast as Dirichlet problem for something else. Then observe what function solves a continuous analog of that, and it turns out that it's solved by a square root of derivative of a map to a strip. And then you should prove that solutions of the discrete problem converge to the solutions of continuous problem. And basically, the well-known subject is Dirichlet and Neumann boundary value, so it's current Friedrichs-Levy as mentioned. So you would want to reduce it to solving Dirichlet problems by some trick. Okay, now we have remaining 6 minutes, and so let's just observe that it is discrete holomorphic. I think it's enough time. So questions? Am I going too slow? No? Well, you see, the thing is, so basically, we will see that for other values of q, f will satisfy half of Cauchy-Riemann equations. So one can say that f satisfies, so Cauchy-Riemann equations, if you do hydrodynamical interpretation, they say that you have a flow of liquid which is divergence-free and curl-free. So you can say that for other values of q, you prove that f is divergence-free, but a priori, in the discrete, it doesn't seem to be exactly curl-free. Approximately, I believe it is, but exactly not. So we have to have a new idea, which I'm searching for, and well, don't see yet. Yeah, so it's. Yeah, we'll see. Yeah, maybe today I will just do it for the easing model. So it's okay. So. So we will actually have a slightly different definition of homomorphicity than before. It will imply the usual definition of the homomorphicity, but well, imply in the sense that well, f is defined as centers of the edges, and centers of the edges, they form a square lattice in their own right, a square lattice rotated by 45 degrees, and f will satisfy usual Cauchy-Riemann relation on this lattice. So what happens for other models is that for other models, f will satisfy Cauchy-Riemann relations for such squares, but not for such squares. So it won't satisfy for square which corresponds to placket here, but it will satisfy to square which corresponds to a vertex here. So that's the answer to Chuck's question. So for easing, some sort of miracle happens is that for every placket of this new lattice, you have Cauchy-Riemann relation, and for other q only for plackets which corresponds to vertices, only half of Cauchy-Riemann relations. Okay. Okay. So there are a few steps, and first maybe I will just observe that f on edges has well-defined argument independently of gamma. So no matter what gamma we choose, these contributions to f, when we pass through the edge, this complex weight will always have the same direction. It might change plus minus, but it always has the same direction. So maybe it's better to rephrase it as saying that f is parallel so f is parallel to vectors which I will write down here now, and these vectors are 1 on half of the horizontal edges, I on the other half of horizontal edges, and lambda on yet another half of the horizontal edges. So it's, let me see, 1i, so it's lambda here, lambda bar here, lambda bar here, lambda here, lambda bar here, lambda here. So f on an edge is not a complex number. It's actually a real number, because where our complex weight is set up such that no matter how we arrive to the edge, we always get the same argument up to 180 degrees. So actually an unknown number on an edge is only a real number. But that's not a problem for us because we've seen that there are these analytic functions which are, say, real on black vertices, imaginary on white vertices, so there is nothing wrong with that we have real number per edge. So this is the first statement. Sorry? Well, I see it very well, but maybe the reason is that I'm colorblind. So it's... No, I mean, it means that I see colors differently. Well, at least I prefer to put it that way. So I think it's perfectly visible yellow color, very bright. Well, okay. No, but I mean, it's sort of perfectly clear. So I mean, since we have something which is rotationally invariant, so suppose that you prove this for one edge. Suppose that this edge will have weight 1. Then when you arrive to this edge, you turn to the right. So the weight has to be lambda bar, because we weight in that way. So it's lambda bar, lambda, I, 1, lambda bar, lambda bar, I. And now I only have to check so that the parity is correct. So I assume that our domain ends like this. So when I exit from this edge, so this is edge B, the weight is 1. OK? Now I have to turn left or right. When I turn right, I have lambda bar. When I turn left, I have lambda. Now here I turn right again, so I have lambda bar lambda, so I have 1. Here I turn right again, I have lambda bar. If I turn right yet again, I get I. So I will prove it tomorrow. Let's leave it as an exercise. No, I prove it now? Well, whatever. So so our interface, it separates clusters on the right and dual clusters on the left. So since it separates clusters on the right and dual clusters on the left, if I cover my lattice into 2 colors, so my curve always has black on the right and white on the left. So when I arrive to some edge, I always know from which direction I arrive. I always have black on the right, white on the left, because my curve keeps lattice on the right and dual lattice on the left. So that's already a relief. And that sort of means that you can just proceed by induction. So this is 1. From it, you can turn left to right to get lambda bar. From this, you can turn left to get 1. Here, you can turn left to get lambda bar. And then you just proceed by induction. So just for example, define such periodic thing and check consistency. If we arrived here and we had weight 1, then whenever we turn left, we would have weight lambda bar. And the only thing we use that black is always on the right in this observation. So this is the proof. Is it OK? No? OK, yeah. OK. The discrete analyticity. So well, OK. And now, well, OK, I will prove discrete analyticity. So there were 2 observations. So one is that F is parallel to those vectors. And the other observation is that if I take 3 edges which are nearby, let me label them north, east, west, and south, that f of west plus f of east is equal to f of north plus f of south. Now, this doesn't look like Cauchy-Riemann relation because you have function which sum with coefficients 1 at 4 vertices is equal to 0. But you have to remember that the function actually, here it is 1, here it is I, here it's lambda, here it's lambda bar. So actually there is complex thing involved. And So this is the second observation. And the third observation is that this equation star, it implies the usual Cauchy-Riemann. So first observation, let's say 1, 2, and 3. And the third is that 1 plus 2 implies Cauchy-Riemann relations. Okay. Yeah, I don't know. Do we stop here? It's up to Vladas. No? Okay, let's. Oh, there is no Vladas. We can have a run at democracy. Ah, there is. Oops. So, do we stop here? No. Okay. Yeah, I have again. I'm afraid to go into the negative on Saturday now. Okay, so let's. So the first is okay. The first is okay. Now the second, well, it's like for the uniform spanning tree yesterday. We have to count configurations. We have to count that if we have that. Let's say, for example, it would be very nice if every configuration would bring the same input to the left-hand side and right-hand side. Well, it does not. You can easily check because there might be configurations where you only pass through two edges and then it doesn't work. But then we can group configurations into pairs or triples or something, and we can do it like yesterday we had this bijection between uniform spanning tree configurations. Now, what we can do when we do this sort of bijections? We have to work only in the neighborhood of this point. We can't really go far away because we will just get lost if we go far away. So we have to come up with something which takes into account only in the neighborhood of this point. Now, what we can change what happens at this point. So what I claim, there are two possibilities for an interface to go through this point. So you can imagine two sorts of pictures. Let me draw them. So one kind of picture is that there is a curve which arrives to this point and then leaves and then goes to A. And another sort of picture is that it arrives to this point, it leaves, then it wanders somewhere, then it returns again, and then it leaves towards A. And what happens is that if we have a picture of second kind where our interface, so this is the yellow interface gamma, if it visited our point twice, what we can do, we can rearrange this connection. If we rearrange this connection, it will only visit it once, and we'll get picture on the left. So so this is our bijection, which we get from rearranging connections at this point. And then I want to see what happens with these two pictures. So let's say this is picture 2, and this is picture 1. And I want to make a big table which says what happens with, let's say, F north plus F south equal to F east plus F west. And so what happens with the pictures 1 and pictures 2? So picture 1 is somehow an easier one because you only have east and south. So we have some contribution to east and some contribution to south. And the bad news, of course, that we don't know the contribution to east because we only see this small part of picture. We don't know whether there are 137 loops or 239. So we don't know individual contributions to east and south. But we know relation between them. Because here, when we move from east to south, the number of loops doesn't change. The only thing which changes is the number of turns we make. And the same, we don't know how many turns we made before, but we know that from east to south, we make additional one turn to the left. So if contribution to east was x in this case, then contribution to west is new, and contribution to south, we make one left turn, and one left turn yields what? Lambda. So you have lambda contribution to south, lambda x. And of course, lambda x is not equal x, except for the rare case of lambda equal 1. But we still have this configuration. And for this configuration, so is it clear what happened so far? So these are contributions of configuration 1 to f at different points. So we somehow, we just to calculate f, we take all possible configurations and see what they contribute. To some points, they contribute 0. To some points, they contribute something else. OK. Now, this contributes to east what? Again, we don't know, but it looks like it contributes the same x because we have the same number of turns. So is it true that it contributes the same x to east? Or has something else changed? Yeah, the number of loops has changed. So here we have one loop less. So this picture has one loop more, and the weight of loop is square root of q. So I have to divide here by square root of q, but perhaps it's better if I put square root of q here above. So we have that. OK. And now when I pass to north, I've turned to the right, and turn to the right nets how much? Left turn lambda, right turn lambda bar. So we have lambda bar x, and south is lambda x. And this is, so it's two left turns, lambda squared x. So you see here, it sort of comes up naturally that our weight, which counts turns, is very reasonable. Why? Because for this part of the loop, we don't know where it was walking around. It made like 2 million steps. So we need some sort of weight which we can compute only knowing that this is a planar loop which started here and ended here. And counting turns is something which works because we know that the total angle circumnavigate is 2 pi if we would have had a connection here. So we know exactly what the weight would be. And now to check our relation, we have to check that the right-hand side sums up to the same thing as the left-hand side. And to do that, we have to find the eraser first. So what we want lambda bar plus twice lambda, plus lambda square root of q equal to 1 plus square root of q plus lambda squared. And that we can rewrite, well, I don't know what's a good thing to do. We can multiply by lambda, for example, to get rid of lambda bar. So, for example, we can rewrite it as lambda cube minus 1 plus square root of q lambda squared plus 1 plus square root of q lambda minus 1 equal to 0. So we have to solve this equation in lambda. It will give us the number with which this works. And it's clear that for every value of q, there will be some numbers. So, for example, number 1 solves this perfectly. But number 1, essentially, solution by number 1, it means the following, that if I take a function which is 1 to the left of my curve and 0 to the right and take its expectation, it will be a function, and its gradient will be rotationally free. So it's sort of an empty observation, almost empty observation. So what are the other roots? So it's lambda minus 1 times lambda squared minus square root of q lambda plus 1. So am I correct? Minus 1. Plus 1. Are you sure? Well, now you got me lost. Yeah, okay. Yeah, no, it's okay. It's okay. Okay. And then the interesting thing, if we remember this trick of Nienhaus, that square root of q was written as exponential of I theta, then I think it should work here. So square root of q is exponential of I theta plus exponential of minus I theta. So that was the Nienhaus trick. Was it our notation? Yes, I think so. Yes. So it's actually lambda minus 1, lambda minus exponential I theta, lambda plus exponential of minus I theta. Did I do it correctly? Yeah, I think so. Yes. Minus, yeah, okay, yeah. Okay, so that's the solution. So there is a solution. There is a unique value of lambda with which this relation works. So unfortunately, what happens, and this is exactly the value of lambda which was chosen by us, because for the Ising model you can check what is the exponential of I theta for the Ising model. So for Ising, what do we have? Q equal to 2. So square root of q is equal to square root of 2, and exponential of I, so theta, is equal to pi over 4. So it's exactly what we needed, or plus minus pi over 4. Okay. So actually, if we take plus pi over 4, we will arrive at anti-analytic functions. If we take minus pi over 4, we arrive at analytic functions. So I prefer minus pi over 4. Okay. Now I think we'll stop here. So we will deduce tomorrow that this is indeed a usual Cauchy-Riemann relation. So you can check you can check that if f is proportional to those vectors and you have such a relation, then you can deduce the usual Cauchy-Riemann relation. We'll start it with it tomorrow. And since someone is bound to ask why it doesn't work for other models, so the second part, it works for every model, as we just observed. It's the first part which doesn't work for other models. So the first part worked for Ising because lambda to the power 4 was equal to 1. For other models, when we walk around the face, we multiply by lambda 4 times, but it's not equal to 1, so we get some other number. So we get a priori complex numbers on edges for other models. So we don't get a nice corollary out of this. Out of this, we only get some divergence-free corollary, but not the full Cauchy-Riemann equations. So that's one way to see the difference for other models. So should I stop here, or do I check 3? Sorry? Stop? Okay. Questions? Okay.